So a very good morning to everyone. MET School of Applied Sciences, MET University, Haryana welcomes all of you to the second day of the National Workshop on Material Characterization Techniques. Our resource persons today are Dr. Chandrasekhar and Dr. C.M. Shrivastava, who will brief us on the theory and applications of thermogravimetric analysis, differential scanning calorimetry instrument. Before starting the first session, let me give a brief introduction to the resource person, Dr. Chandrasekhar. Dr. Chandrasekhar is working as an assistant professor in the Department of Applied Physics, MET School of Applied Sciences, MET University, Haryana. He obtained his MSc in Physics and MTech in Materials Science from Barkatullah University, Bhopal. He completed his PhD from Department of Materials Engineering from Indian Institute of Science, Bangalore, and thereafter worked as postdoctoral fellow at the Department of Mechanical and Industrial Engineering, Concordia University, Canada. Dr. Shekhar has published 35 research papers in international journals of repute till date. His research interests are phase equilibria and thermodynamic CALPHAD modeling, nanostructured thin films for gas sensors, solar photovoltaics, and dielectric properties of materials. Now I request Dr. Chandrasekhar to please unmute himself and conduct the session on Introduction to DSC and its applications.
Thank you, Dr. Anurag, for the nice words. So good morning all. Today we'll be discussing about the differential scanning calorimetry, one of the main thermal technique that is used to characterize the materials. So let us start the topic. This is what the instrument that we have here at MET School of Applied Sciences, which is known as STA. DSC or differential scanning calorimetry is the most widely used this thermal technique among the various techniques that are available for the material characterization. And various type of materials, whether they are plastic, foods, edibles, pharmaceutical, glasses, ceramics, amorphous material, biomaterials, alloys, superalloys, pharmaceutical, all sorts of material can be characterized. The materials that undergoes any transformation that react to the change in the temperature or increase in temperature, all such material can be characterized, and transformations or transitions or reactions can be basically looked at by this technique. What exactly is the principle? The principle of a differential scanning calorimeter, or the technique as such as the differential scanning calorimetry, this measures the heat flow. So there is the particular control environment in which the sample is kept, and either from the sample to the environment or from the environment to the sample, there is a heat flow. There is a flow of heat depending upon what is the condition of the sample. So this heat flow is measured, or rather it is the temperature is measured, and the through the transfer function the heat flow is determined. And this heat flow that occurs in the sample, when this sample is subjected to the temperature program, which could be the heating of the sample or cooling of the sample, or even the isothermal, when the sample is kept isothermally, that means at a constant temperature for a predetermined length of time. So this is the calorimeter, and the technique is known as differential scanning calorimetry. By this energy change, we can find various kind of transition that are occurring in the sample, quantitatively as well as qualitatively, and to know the temperature where these transitions are occurring, or that particular transition characterize the behavior of material, including but not limited to melting in the, say, crystalline materials, inorganic material, then and the amorphous, the glass transition temperature, and various other more complex transitions that will be looking in the slides to come. So basically, there is a heat flow, there's flow of thermal energy from the sample to the environment or vice versa, and this thermal energy is monitored very precisely, very accurately, and this flow is kind of correlated with what is the behavior of the material in that particular temperature range. Okay, so this particular technique is differential calorimetry. Now going to the actual the words differential scanning calorimetry. We know, if there's a temperature range, so there's a heating or cooling. This particular word say differential, then scaling, then calorimetry. So when there is a thermal energy flow rate is measured, I mean the thermal energy flow rate is measured. This is what is the calorimetry. So calorie, we know this is the unit of say energy. So when thermal energy is flowing, the rate of that flow is calorimetry, and we are changing the temperature. So when there is let's say this measurement is over a temperature range. Okay, so then we are basically scanning from say low temperature to high temperature, and during this temperature change, what is the change in the thermal energy flow rate? Okay, so that becomes the scanning and then calorimetry. But when we are measuring this flow rate from initial to the final temperature in comparison to something which is inert, which doesn't change, it doesn't react, it doesn't transform in that given temperature range, then this comparative measurement of thermal energy flow rate from lower temperature to higher temperature in the thermal temperature program, which is predetermined, is known as the differential scanning calorimetry. Okay, so essentially there are two things. One is the sample, and other is the inert. If you look at this is the inert reference. Okay, so now if you look at the image on the right, we have this is the sample, and this is the on the right there is a reference. Okay, so what actually happens if you look at these red dots, this represent the furnace or the heating elements of the furnace, and this is cylindrical box or cylinder is represents the furnace. So this sample, the sample crucible and the reference crucible is kept in the furnace in the control environment, where you have sample sensor, reference sensor right at the bottom of the crucible, and this entire sample and reference is kept in the furnace, and there is this furnace is being heated. Okay, and there's a inert gas that is flowing, which is known as the preheated purge or purge gas. And then there is a coolant that goes that to keep the change in the temperature controlled. Okay, so this is what is the differential scanning calorimetry, and the literal meaning and how the apparatus looks like. Okay, so if you look at now, if you simply take an inert material, suppose this and in a predetermined heating rate, that inert material is heated. Okay, so since it is inert, nothing will happen, and only the temperature of the this particular inert sample will increase. So this black solid line represents say the temperature. On the y-axis there is temperature of this inert sample as a function of time. Now time, because the heating rate means the change in say temperature per minute or per second. So this is the heating rate. So when we have fixed heating rate, we know at say given length of time what is the say temperature of the sample. So the x-axis, though the unit is time, the variable is time, but we know what is the temperature. This time represents the temperature of the environment, the furnace. So if there is a say inert sample, nothing will happen, and simply based on the heat capacity of the reference, the temperature of the reference will increase, right? So this is what is the solid thick line. Line represents the reference. Now suppose there is a sample whose properties, whose thermal behavior, whose response to the temperature change we are not aware, we don't know. Okay, we don't know exactly. So if that reference is subjected to the same temperature scheme, temperature program, so it will happen again depending upon its heat capacity. The temperature of the sample will increase until there is some transformation. Now, if we have taken an example of melting here, so when there is a transformation, say from solid to say liquid, so depending upon what is the latent heat of say transformation, that much energy per mole will be absorbed by the sample, and the thermal energy will be used to transform the say solid to melt. And during this process, the temperature will remain constant. This line shows the temperature of say transformation. Once the transformation is completed, because furnace temperature is increasing continuously, or say which represents, this is the say temperature of the chamber of the furnace, this is increasing continuously, and the difference in the temperature of the furnace and the sample, once the transformation has completed, this has actually increased. Okay, increased, and to catch up the temperature of the sample, which is now transformed, say now it is melted, it catches up, and after some time actually the temperature of the sample as well as the reference follows the temperature regime. Okay, so this is quite obvious. We can basically, if we follow the temperature of the sample, we can identify that at particular temperature, the temperature of the sample was fixed at a particular point, and then it accelerated. It increased with a quicker say speed. So at that particular time, there is a transformation. Okay, but if we don't have the inert sample, then the resolution of this event is not that good. Okay, so if we have the reference, we can simply subtract the temperature of the reference and the sample, which is there being monitored simultaneously, and what we end up having is something like this. So this is the delta T. This delta T is the, so suppose this is the sample and this side is the reference, and these two thermocouples which are measuring the temperatures of the sample as well as the reference, they are connected in a differential manner. What does it mean? The negative of one thermocouple is connected with the negative of the other. So in this case, the total temperature or the difference in the EMF is generated as output. So which is proportional to the temperature difference between the sample and reference. What does it mean? It means whenever there is a transition, for example, melting here, the difference between the sample, the temperature of the sample and the reference will be more, and this delta T, value of delta T will be more, depending on here it is melting, so it is the say endothermic process, and if there is exothermic process, there will be a peak upward. Okay, depending upon the transformation temperature, this could be lower variable temperatures. So the idea is, depending upon what is the transformation, there is a lag, there is a difference, there is the sample's temperature lags behind the furnace temperature, and this temperature difference is used to generate the information which represents the delta T. Okay, so if this delta T is plotted say as a function of time, we get a peak. So this very idea is expanded to accommodate various other transformations, including reactions. This example was only for the melting, but all other example that we listed in the slide above, that can be accommodated. Okay, so this is the difference in the temperature. Gives a peak when the temperature difference is plotted, and the example is for endothermic event. And this endothermic peak having a downward, it could be, I mean, it depends upon model to model. In some models, it is upward as well. So the various type of physical and chemical processes that um, can be looked at by DSC is absorption, which is the exothermic process, and desorption, the opposite of the absorption, is an endothermic process. If there is a phase transformation, change in the crystal structure, which could be endothermic as well as exothermic process. This is basically solid to solid transformation. There is crystallization when you have the melt, then that crystallizes to give to have the exothermic peak, and then melting, as we just saw in the last slide, vaporization, sublimation, oxidation, reduction, or there are reactions, chemisorption, solid-solid reactions, etc. Okay, so basically there's a whole spectrum of the transformation, which basically takes the same idea that whenever there is a any of these processes happening in the sample, there is either the thermal energy generated or it is consumed from the surrounding. So that creates the difference in the sample temperature or the with respect to the temperature of the furnace, and this temperature difference is used to generate the information which is proportional to the event that is occurring in the sample. But this is though the DSC technique is can detect all sorts of these events, thermal events rather, but it is not also, I mean, there are techniques that are required. For example, it can the DSC can tell you that something is happening in the sample. Okay, that is related to the thermal event. That's the generation or consumption of the thermal energy. But what exactly is the transformation that need to be confirmed with the other techniques? For example, if there's a structure change, that X-ray diffraction needs to be looked at. If there or spectroscopy or microscopic investigation is required, or so. This is again we can look at the glass transition temperature in amorphous materials, the crystallization time, how quickly the crystal is forming, or how much at what temperature the transformation is occurring. This is especially important in case of the thermodynamics, phase equilibria, or the stability studies, etc. of these materials. Sorry. We can calculate the percentage crystallinity in the say polymers, heat of fusion and heat of reaction, specific heat capacity of the given sample, then curing in the polymers, interlinking, reaction kinetics, purity. That's very important. This purity of any compound, any alloy, any element can be detected, can be indirectly looked at by using DSC. There are phase transformation. Now, what are the different type of DSC these instruments? Okay, look at the DSC instrument as such. There is this heat flux DSC. If I just go back to the earlier slide, we got the y-axis, there is delta T. If the thermogram, the graph that give you the information of the thermal event occurring in the sample, if there is a delta T versus temperature or time, then this is basically known as the thermogram for DTA. So there is basic difference between DTA and the DSC. Though the working principle is same, but the information that is extracted that is a little different. So if there is a delta T, please remember, if there is a temperature difference on the y-axis, this is the thermogram for the differential thermal analysis. Okay, so terminology remains the differential because there are two, thermal analysis because of the temperature difference between the two. If you are plotting directly the temperature difference, but if we are looking at the DSC, the definition of a DSC we have given is we measure the thermal energy flow. So thermal energy and temperature difference. In the DSC, there is a transfer function, there is a calibration. If you look at the image here, there is a calibration of the instrument that basically correlates the temperature difference. Let's say initially the temperature difference is measured, but then that temperature difference is correlated to the thermal energy flow. This process is calibration, and this is very specific to each instrument. And the after the calibration, the conversion of the temperature difference into the thermal energy flow is given in the manuals of the instrument, and the same is inbuilt in the software that processes the data. Okay, so this basic difference between DSC and DTA, once it is clear, then there are basic two different categories of the DSC. The first one is, say, heat flux DSC. Now heat flux, what it does is we have the same furnace. Okay, the sample we have here at MIT School of Applied Sciences is the heat flux DSC. So what happens in this? We have one single furnace. If you look at the image on the right hand side, so there is a single furnace, and both sample as well as the reference is kept in the same furnace, and this the temperature of the furnace is programmed, and then delta T is measured, which is after the calibration, the transfer function. This delta phi SR is plotted as a function of time or temperature. So the main difference now is the delta T phi SR. This phi SR represents the thermal energy flow rate. Okay, so if there is this basically this is the power. If you look at the y-axis, this is milliwatt, and on the x-axis there is this time or the temperature of the sample. Okay, so in the heat flux DSC, both sample and the reference are kept in the same furnace and subject to the predetermined temperature program, and then the thermal energy flow difference is measured, monitored, and that is correlated to the thermal event that is happening in the sample. So in the heat flux DSC, there are these disk type measuring system that is given here, and in this disk type, both the sample and the reference are kept on the disk. There is a thin disk of the conducting material in which the sensor which detects the temperature of the sample as well as reference is monitored. So in the disk type DSC, the crucibles and the specimen are positioned on a disk made of metal, ceramic, or similar materials. The temperature difference between these two is measured between separate sample and reference, and then this temperature is integrated with the disk or the connecting disk. So depending upon the geometry, there is this type heat flux DSC. If there are two kind of the sample and reference are kept in the same furnace, but there are different these thermophiles, and there are different chambers or known as the cavities for the sample and reference. So that kind of arrangement is known as cylindrical type system. Okay, so in a cylindrical type DSC, the furnace is provided with two or more cylindrical cavities. So basically there are only two cylindrical cavities, for each for one for the sample and other for the, say, reference. And a specimen is directly or suited is placed in these cavities or in the suitable crucibles, and the thermophiles or thermoelectrical semiconducting sensors are arranged between the two hollow cylinder or these furnaces. So if what you will look at the zigzag pattern is the arrangement of the thermophiles. So in the earlier case, there are thermocouples, and in the later in the disk type measuring system, disk type heat flux DSC, there are thermocouples, and in case of cylindrical type heat flux DSC, there are thermophiles. So thermophiles, because of their more contact area, more contact points with the say this cavity, these are more sensitive, and more sensitive to temperature, and therefore the temperature that is measured by the thermopile is more say correct. So that way the cylindrical type system is have higher resolution for the temperature. The other second type of the DSC is the power compensation. Now this is actually important. What happens in the power compensation DSC? First difference is there are basically two heating chambers. One is for the sample, other is for the reference. So the idea is there is a inert reference. We know nothing will happen to that inert reference in that particular temperature range, but the sample can undergo transformations, right? So the temperature of the sample and the inert is kept constant. Okay, in order to do that, what is required? We need to either give a lesser amount of thermal energy, or we need to heat the sample. Okay, so this is kind of a reverse than the heat flux DSC, where whatever is happening, we are simply measuring the temperature difference. In power compensation DSC, we are compensating power. If there is a endothermic event, then the extra power is given to the sample. If there is an exothermic event, then the power given to the say sample is withdrawn. Okay, proportional to the energy generated or consumed by the sample. Fine. So this is kind of power compensation. So what if you look at the if you look at the signatures of the event, same kind of event in power compensating DSC and heat flux DSC, what you will see, the say endothermic event for the power compensating DSC, it will go up, whereas in this type it will in the heat flux DSC it will go down, because in power compensation DSC we are not measuring the temperature of the sample and reference, but we are monitoring the power given to the sample in comparison to the power given to the reference. So the difference, suppose there's exothermic event, we need to give lesser power, so then the peak will go down. Okay, so suppose this is the endothermic event, so there is additional power that needs to be given. So that way this is the peak is opposite to that of the heat flux DSC. But what is important here? Important here because we are monitoring the power directly. Okay, and we don't need the transfer function to convert the temperature difference into the thermal energy flow. Fine. So power compensating DSC are again have the represents the thermal event more accurately than the heat flux DSC, but then because of the complexity of the instrument, this costs more. Okay, so there are give and take in the both type of the instruments. These specimens are arranged to two separate cells. This is the same thing as written here. If we so if we look at the output from the power compensating and the heat flux DSC, as we discussed, the thermograms that are generated from the heat flux DSC and the power heat flux and power compensated DSC, the signatures are opposite. Though these two events are similar, but you can see the heat flow. For one it is positive, for other it is negative. It's the same event depending on what kind of instrument that is used. This curve is for nylon from the double furnace DSC. Double furnace DSC is power compensating DSC, and the single furnace DSC, this is heat flux DSC. So for the different instrument are giving kind of opposite peaks. Now let us look at what are the theoretical consideration as far as the evolution of heat from the sample goes. So there is a simple approach given by Gray in way back in 1968. He gave a very simple transfer equation which gives the general formula for the DSC signal. Now this is DSC signal is the thermal energy flow rate, and So the instrument signal in response to the evolution of heat from the sample. If there is some thermal event happening in the sample, what is the DSC signal, how that is generated, and so on. That equation was given by Gray, and this equation is given here. So this is the thermal energy flow rate, and this is this is the heat flow between the thermal energy source and sample. So initially, between source and sample, it's considered at zero in the equilibrium, and depending upon the heat capacity of the sample and reference, and then dP by dt is the is beta, which is the heating rate, that is also constant. This determines the heat capacity displacement. You might have seen, we'll see in the slides to come. If because of the temperature heat capacity difference in the sample and reference, there's a the displacement in the curve. There's a slight shift in the curve as the temperature proceeds. So this is due to the difference in the heat capacity of the reference and the sample, and depending upon what is the dq by dt, what is the heating rate, there's a thermal lag, and this thermal lag is because of the heat capacity of the sample and the how quickly, what is the thermal energy flow rate between the sample and the source. So there are these three terms. This is not exactly this doesn't, you cannot calculate the DSC signal from this equation, but this using this equation, the underlying mechanism can be understood quite clearly, and the instrument can be calculated accurately. So CS here, the heat capacity of the sample, then CR heat capacity of the reference, source of the thermal energy, which is the furnace. That is temperature of that particular furnace, or the program temperature. Okay, and R is the impedance between the source and the sample. So suppose there is this is the furnace that surrounds the sample. So program temperature is, suppose that is TP, and there is a particular atmosphere, inert gas atmosphere, and then there's a thermal energy heat capacity of the crucible sample holders. All these factors are accommodated into what is known as the thermal impedance between source and the sample. So how efficiently the thermal energy from this furnace is transferred to the sample is given by this R, and dt is the thermal energy flow rate between the source and sample, and beta is the heating rate. So using all these factors, using Gray's equation, the underlying mechanism that determines the DSC signal can be approximated. Okay, and during a particular transformation, when Gray gave a gradient. See, initially in equilibrium, there is suppose there is nothing happening, but during the transformation, melting, sublimation, vaporization, etc., and there is a endothermic or exothermic peak, the initial gradient of this slope can be calculated using the equation that is given here. So this is about the basics of the DSC. Now we'll go to the instrumentation. The instrumentation requires, there are distinct parts of the instrument. One is the purge gas. This is the inert gas. It could be inert gas, could be nitrogen, could be say helium, could be oxygen, depending upon the experiment to experiment, and at a steady flow rate. Now this purge gas, actually what it does, there is a furnace that is heating in a certain temperature range. This purge gas being inert, it takes out any volatile, corrosive, or any gaseous product that is generated because of the which is generated from the sample. So this basically prevents the long-term damage to the sample. And because if there is a volatile species that is being generated, it may corrode, it may deposit onto the sides of the chamber, because the temperature sensor are very sensitive. Thermobalance is very sensitive. So these vapors that are generated in the chamber need to be taken out. So inert gas is at a constant rate, continuously flowing through the chamber during entire heating and cooling cycle must be there. So then this gas cannot directly go to the gas chamber. There's a dehumidifier that is required. So gas need to be, this gas should be 99.9 at least. At least this is the purity that is expected. Beyond that, if suppose it's just 99%, that's not advisable. So this humidifier basically cleans out any moisture that is there in the gas, and this flow rate, which is maintained at 2 bar. And then the most important thing is the furnace. This is a, you have written, it's a consumable item. So this must be operated only at the room temperature. Operated means when you are putting the sample, taking out the sample, or if not at the room temperature, never at the temperature which is higher than say 40 degrees centigrade. Okay, so it must be used very judiciously. The other component of the instrument is coolant or the chiller. So chiller basically, because we need to cool down the temperature, cool down the furnace from whatever high temperature we have subjected the samples to. So coolant is very important. Again, like the purge gas, coolant is also necessarily required to be flowing through the instrument all the time. The mass flow, the coolant flow rate controllers, they are already inbuilt in that in the instrument. So like the gas, there is no need for the controlling the flow rate of the coolant. Distilled water must be used in the chamber, and the temperature of the coolant must be lower to the lower than the room temperature. So for example, if the coolant is at 5 degrees centigrade, from 1600 degree centigrade, the furnace can be cooled under 35 minutes to room temperature. Okay, so the temperature of the coolant is important. And then thermobalance. What you see on the right here is the thermobalance. This is like 6 to 7 centimeter long. So this is not very long. We'll see during the demonstration today how long it is. So this is very delicate instrument. This thermobalance. On top of this, this thing goes down, and at the end there are the sampler reference that is kept. So thermobalance must not be mechanically handled at all, neither forced, twist, remove unnecessarily. And this is the most expensive item of the entire business, the instrument. Then of course there is a data acquisition and data analysis, which is done by the software. So this is the what are the instrument basically looks like. There's a purge gas, the nitrogen cylinder, and then it goes to a dehumidifier. Then this is the ST instrument, and then this is the chiller, and then connected interfaced with the PC, and where the data acquisition and data analysis is done. And the other important component of the instrument is the crucible. The crucible of say alumina crucible, and this is platinum crucible is shown here. Other crucibles, for example, aluminum, this nickel, copper, and quartz are also used generally depending upon the type of sample, depending upon the nature of the sample. So this alumina crucible are largely, aluminum crucible are largely inert at the lower temperature, and they do form solid solution with some metals. And to prevent that, the aluminum crucible is generally subjected to be heated at 400 degrees centigrade for 1 or 2 hours in air, in order to get the alumina coating onto the surface of the aluminum that acts as a protective coating. These alumina crucibles can go up to 100 degree centigrade, and beyond that, the platinum crucible can be used. And needless to say, the crucible must be clean, especially from the bottom. So, what is on the left hand side bottom? This is the top of the thermobalance. On top of these, the crucibles are kept. If there is some sample, some residue, some impurity is there at the bottom of the crucible, it may get trapped onto the thermobalance, and because thermobalance is also subjected to the high temperature, there may be some reaction, some formation, some unwanted residue onto the balance, which actually is not advisable for the as far as the life of the thermobalance is concerned. The crucible, I mean, the sensitivity of this thermobalance is 0.2 microgram. So you can assume how sensitive it is. So it has to be, the crucible has to be put on the thermobalance and removed from the thermobalance very, very gently. Okay. And in case of the these non-volatile samples, only the very low quantities should be used. The sample should be non-volatile, and the appropriate amount should be used. And in case of the sample having high vapor pressure, we will show these crucibles can be covered with the similar material, the lid of the crucible, in order to prevent the loss of the material because of the high vapor pressure. And if the material is high vapor pressure or volatile, then hermetic pan can be used, which essentially is suppose this is aluminum crucible. On top of that, aluminum cap is kept, and that is mechanically pressed, mechanically sealed basically. So this is and at the top of this encapsulation, there is a small hole that is created in order to equilibrate the pressure. So in that manner, the sample which are high vapor pressure, having high vapor pressure or volatile, they can be characterized using DSC. These are the requirements why a purge gas must be used, because it provides a dry and inert atmosphere, and it protects the DSC measuring cell to achieve good reproducibility. It ensures heating and the heating chamber, good heating, even heating. Also, it's basically the purge gas removes the dead volume in the cell. It helps to sweep away of the gases and that might be released up to 600 degrees centigrade. Nitrogen is a common inert gas that is used. It increases the sensitivity. The flow rate is suggested 20 milliliters per minute. Other gases, for example, oxygen, to determine the oxidative behavior of any material, and the helium. Basically, helium is used to separate closely lying peaks. There are two transformations. For example, there's a eutectic alloy, and which is close to the composition. So generally there are two peaks that are very closely associated. They are very close to each other, and in order to separate that, helium as the purge gas can be used. These are the specifications. So I will. What important is, this is the top loading. There are side loading, bottom loading DSC also, and the one we have is the top loading with the balance resolution of 0.2 microgram, and it can have the balance can measure up to 1500 microgram, and the furnace can go to 1600 degrees centigrade with the heating rate of 100 degrees centigrade per minute up to 1000, and beyond 25 degrees per minute. And the cooling rate are good under 35 minutes if the cooling water or chiller temperature is 5 degrees centigrade. The calibration of the instrument is generally done using indium, gold, or palladium, and the temperature accuracy is up to 1000 it is 0.5 degrees centigrade, and beyond 1000 it is 1 degree centigrade. And the calorimetric accuracy is 5%. Balance precision is 0.02%, and the platinum rhodium type thermocouple is used. It's a quite light, 14 to 17 kg, and we have the fire software. Okay, so this is about the instrument, and now the operational parameters. There are operational parameters that basically are important. What is the heating rate that is used is very important. It basically, either if there's a high heating that is required, so the transition may overlap, and that may cause the interpretation problem. Then the other important parameter is the equilibration time, because this is a very sensitive kind of thermobalance. So even the small change in the purge gas flow rate disbalances this thermobalance, and it generally takes a few minutes to come to the equilibration state. So equilibration is very important, and generally half an hour to 45 minutes is required for the initial equilibration each day. Then because if the water as a coolant is used, then cooling times becomes important, because it takes more than the time that is specified, because the cooling liquid is generally not at 5 degrees centigrade. Gas pressure is important, because in order to flush out whatever is generated gaseous byproducts that are generated in order to flush, this gas pressure is important. And the most important is the standard operating procedure of the instrument should be followed all the time. So this is the differential calorimeter diagram given on the right, and how much time do I have? Okay, I should move a bit quickly. So there is a linear heating and the modulated heating. This program is given for the same type of transition. What we can see here is for a material, if the linear heating rate is used, the peak or the resolution of the peak is very much enhanced when the modulated heating is used. So this feature is generally available in the advanced data acquisition software. But this is very important to increase the resolution of the peak or the thermal event that is happening in the cell. So how do we basically look at a peak, and what are the different parameters that are set? So there's the onset temperature. This is the temperature where the transition is thought to be starting. Suppose you are determining the melting point or boiling point. This onset temperature is the temperature where which actually determines the melting point. Then we have on this on the left hand side, there's a first tangent, and the right hand side there's a second tangent. Whenever wherever these two tangents meet, there's a extrapolated peak, and otherwise this is extrapolated at the top, and at the top of the correspondingly the top of the data is the actual peak, and there's a onset, and the corresponding there's a end set. Okay, this is for the peak, whether it is exothermic or endothermic, same approach goes. And for the glass transition temperature, there is this tangent there. So there's a tangent from the onset. Is a slope, and then there is a baseline, and in between, depending upon the midpoint or the inflection point, there's a tangent that is drawn, and the point of intersection of the onward and the baseline tangent determines onset and the end point, onset point and end set point. Okay, and these are similarly are determined for the are used for the designation of the particular event. For a given endotherm, there are various type of processes that may happen. For example, in case of say polymers, initially there is a glass transition. The heat capacity of the polymer changes, and that is represented in the kind of stepwise transition in the thermogram. And if there's a polymer, it may crystallize, giving the crystallization peak, which is kind of exothermic on the upward side in this case. And once the corresponding melting point is achieved, there's a endothermic peak, and beyond that there may be curing or cross-linking of the polymer and maybe oxidation. So there are various processes that may happen in the material, and correspondingly there will be signature of that process in the thermogram. If you look at the various type of events that happens in the curve, so for example, suppose we have a pure substance, basically non-polymeric pure substance. There will be a sharp kind of the onset and this slope will meet at a given point. The onset temperature will be as close to the actual data as possible. So that represents the pure substance. And if you have a eutectic impurity, you will have the small endothermic peak close to the actual peak, and this represents the eutectic material, eutectic impurity that's represented in the sample. And if there is an elongated kind of slope, as in this T, then there's a plastic which is semi-crystalline. And in case of if there's a exothermic event that is associated after the endothermic event, so that represents this melting with the decomposition. So after melting, there's a decomposition in this case, and there may be melting with the decomposition, but that is exothermic event. So, and in the liquid crystal, there may be some phase transition, and this kind of small endothermic peak may be found in case of liquid crystals. There are in the cooling curves, for example, if we have the pure substances with a low melting point, then or the super cooled liquid or droplets that solidifies at a different time, so we have kind of a very closely packed peaks. Or if we have this cooling of the eutectic impurity, we can see exactly reverse to what we have on the left, B curve B in the left hand side. And if there is a kind of a material which is plastically deformed, and once that is heated, there will be crystallization, and once there's a crystallization, then let's say there's a glass transition or the cold crystallization. So depending upon what kind of material, from the peak we can actually determine, we can make a very good guess that what kind of transformation is happening. For the interpretation of the curve, the baseline is very important, determination of the baseline. So baseline, this is the baseline. So for example, if there's an endothermic event, so connecting the start of the points at the start of the event and the end of the event is the good enough. This baseline one is not recommended. In the B, again, having just a horizontal line is not recommended. We must have a spline from the start of the point to the end of the point, and then do the necessary calculation as given in the C. In case of the melting and the event where melting and decomposition are associated, a horizontal line is what is recommended, not a curved line. Curved line will accommodate the decomposition at this particular point as the baseline. So it will suppress the information corresponding to the decomposition of the material. And if there are two transformations that are happening at the close, very close temperatures, for example, in case of eutectic alloy, so the baseline is generally what recommended is the horizontal line in this case. Also, if it is along the two, that is also good enough. That actually separates the peak, but suppresses the information corresponding to this peak at corresponding to this particular area, which is this particular region. So both approaches to correct the baseline have been used. These are depending upon what kind of the processes are going on. There are various processes also. For example, this is the glass transition. This is glass transition with a small this enthalpy relaxation, and then in case of reverse transition as the glass transition, and then this is the Curie transition in case of the magnetic materials. So what are the comments for the interpreting the curves? The in case of uncertainty in the DSC curve interpretation, there should be corresponding the instrument or the sample should be subjected to another characterization technique, and then it should be correlated. And this should be done. Generally, it is done as in our case. It is a thermogravimetric analysis that we'll have in the next session, or the thermodynamical mechanical analysis, where mechanical behavior of the material is generally looked at as a function of temperature, or the evolved gas analysis, Fourier transform, or mass spectroscopy, etc. Okay. So what are the applications? For example, let us look at suppose there is an endothermic or exothermic event. So we can calculate the total enthalpy change corresponding to a particular event just by integrating the peak from, say, time t1 to t2. We must remember there's a integrating with respect to time. The curves which are plotted as a function of temperature also, for example, in this, must be integrated as a function of time. So there are various steps: define the baseline and then select the desired temperature and time, then do the integration. On the similar lines, the content, suppose there is a mixture. there are mixtures whose the content composition need to be generated, so that can be approximated DSC very effectively using the relation. So we need to have the pure the DSC curve for the pure one of the component in pure form should be characterized using DSC, and in comparison to that transition, the transition of the given sample must be correlated, and that way the content can be calculated. In order to determine the crystallinity of the sample, the crystallinity again can be approximated using the same this mathematical formula, but in case of the pure, which is the delta say 100, there are literature values for given, say, polymers, for polyethylene, polyethylene, low and high density polypropylene, polyamide, etc. These values given the literature must be used in place of delta H0, and then the crystallinity, degree of crystallinity can be determined. If there is a, suppose there are reactants that are the reaction or the two reactants reacting to product, that can be determined using a similar relation. So whether there is a first order transition or chemical reaction, that generally can be determined by what is known as the conversion, and this conversion is proportional to peak area. For example, on the image on the right gives the liquid fraction of say cocoa butter. So from this, as a function of temperature, there's a fraction from as a 24 degrees centigrade, very small fraction is converted, but at up to 38 degrees centigrade, almost 99% of the reaction has occurred. In case this starting point is 0, but sometimes it may not start at 0. So to accommodate this, there are this other mathematical relation that is given that takes the delta H from the literature for the total and partial, and then it converts the. The other important application of this is the specific heat, measurement of the specific heat. There are various methods. Okay, there's a direct method. There is the method using the sapphire. So this is direct. In the direct method, the flow rate is divided by the heating rate, and then the weight of the sample, and that gives us the heat capacity. That is the direct method. But in this case, there are basically the empty pan, with the reference and the sample. There are three curves that are required, and they are specifically used as given in this. So there is a particular standard in the ASTM, the E1269-11, that is used to determine this specific capacity using DSC. Using sapphire, generally the heat flow rate for the sample for the sapphire and their respective masses and the heat capacity of the sapphire is used in order to determine the heat capacity of the particular sample. A purity of the sample can also be determined, because if the sample is impure, there's impurity in that, there will be shift in the peak as given on the right hand side, and again corresponding to the pure one, the purity of the sample can be determined, say in this 97%, 98, and 99.9. So there are various steps to determine the purity, and okay, so these are the methods to determine the heat capacity. So direct method, sapphire method, ISO step. Basically, what is changing is the temperature program to which the sample is subjected. If it's a linear direct method, sapphire method, there's the equilibration at the start and end, and the end in ISO step there are seesaw kind of variation, and then the steady state, and this is sinusoidal, and then it is random. Okay, so in hindsight, if you look at the applications of the DSC in various spheres, so specific heat, enthalpy, what we need to look out, for example, as we discussed in majority of the points. So for the say enthalpy of fusion and crystallinity, we need to integrate, calculate the area under the cup, and then compare with the 100% pure. For the glass transition, the glass transition step that is determined, and so on. So there are quickly I will go through 2-3 these examples. For example, this is the example for tetrahydroketone, PEEK. So this shows very nice glass transition at close to 150 degree centigrade, and thereafter there is a crystallization, and after the crystallization, then there is melting at 339 degree centigrade. So glass transition, crystallization, and thereafter melting happens in this case. And if you look at the tetrathalate or PET, again there is a glass transition. This glass transition is associated with the enthalpy relaxation, and then cold crystallization, and then there is a melting. So various these parameters can be determined, and this is the example for determine the enthalpy of decomposition of the zinc carbonate. So I'll quickly go through this. So what are the precautions? One of the first steps to ensure the good data is to keep DSC cell clean. The furnace, the thermobalance, the crucibles, everything should be clean, and it should be handled very, very carefully. That is the first thing. And the sample that decomposes during the run, that should be known prior to that, and the only small amount of the sample should be used. And if it is decomposing, TGA analysis should be done prior, and the temperature should be limited to till before the decomposition. It should stay below the decomposition temperature, and sample should not spill off the pan, and it should be never be at the bottom of the crucible, and it should be clean. And in case required, say lid must be used. What are limitations? Limitations, it's a very sensitive thermobalance. It is a limitation in the sense then while using the thermobalance, one should be very, very careful. One small mistake can ruin the entire instrument. The long cooling times at times, that is again a limitation. But to address that, there are fast scan DSCs, and equilibration times that this is the nature of the instrument. We cannot eliminate that. We need a lot of patience to get good results. It's very sensitive to the mechanical vibrations. Mechanical vibration can especially affect the thermogravity these results. And for the sample preparation of the volatile samples, little difficult to prepare the harmite cells, and or difficult to differentiate the transition having the closely related transitions. These are the references, and I thank you for your attention. I'll be happy to take questions if you have. I think I have exceeded the time.
No, I think that is okay, Dr. Chandrasekhar, because you have conducted such an informative session wherein you have briefed us about all the aspects of the instruments. And I'm sure participants learned a lot in this session. So as you said, may we have some queries on the...
I'll be happy to take the questions.
Yeah, so any queries, it can be very simple, complex, you know? If it comes to your mind, then it's a relevant query. Okay, there's one from Rohit Yadav. He says, if our sample is inert, yeah, just a moment, I'll try to read it out. So he says, if our sample is inert in temperature range, so then can we measure the heat capacity?
Oh, sure, we can measure the heat capacity. If it is not inert, then the heat of transformation, or the latent heat of that particular transformation, can be determined along with the heat capacity. So because the inert samples do have heat capacity that can be determined. It's no issue in that.
And there's a question from Anand Selvi. He says that can you work on proteins and differential scanning calorimetry? Do you get a peak for protein molecules? Protein molecules.
Okay, I think if there is any energy exchange, okay, if there is any energy exchange between the various forms of protein, that can be seen. I don't think because the instrument doesn't differentiate between the samples, any kind of sample which are not volatile to the crucible, that can be used, and definitely we can see these peaks. How to get the peaks? Whenever there is a transition which is associated with the thermal energy exchange, then you will get a peak, irrespective of the type of the sample. If it is not volatile,
yeah, that is true. That is correct. So Anand Selvi, you can work on proteins and DSC, and probably get very good data on, say, protein unfolding, or say protein aggregation and so on. Yeah. So any more queries? You can type in the chat box. Manoj Kumar says, I don't exactly understand it. He says, what is the range for polymers? Now he's talking about
the range.
Yeah.
What is the range of the polymer? Okay, I think he's talking about the temperature range. So for the say if you're talking about the temperature range is suitable for the polymers, as we have we have on screen, it is a polymer. So polymers are basically stable till low temperature. So one should not go beyond the melting, but with the polymer do stick with the crucible surface. So generally we tend to be at the temperature that is lower than the say melting temperature of the polymer. But with the proper cleaning, that can also be done.
So there's a query from Preetham. I don't exactly understand it. So
okay. Is DSC detect the weakest thermal effect? Yeah, it can detect depending on what is the amount of thermal energy exchange. Suppose the weakest effect in terms of the say latent heat of the transformation can be detected if it is more than the sensitivity of the instrument. If it is less, we can have little more sample, but not beyond the capacity of the crucible, and it should not expand and spill off. If it is the sample doesn't expand during the temperature program, it can be the amount can be increased so as to be great. The thermal energy exchange is greater than the sensitivity of the instrument, and then it can be detected.
Yeah, so there's a query from Brijesh Kumar. Yeah.
Okay. Is it possible to have both options? Okay. in DSC, exothermic
No, before
cells or TX.
before Rohit.
So this peak same under DTA curve.
No. I'm sorry to interrupt you. There's
Yeah,
a
please.
before that from Brijesh Kumar. He says heating is continuous or can it be transient?
Heating on the setup, heating is only continuous. No, we can have the isothermal breaks as and when. I mean, that method we will describe in the demonstration in the afternoon. We can program as desired. We can increase at a increase or decrease. Basically, we can change at a desired rate. We can have the seesaw kind of the heating rate as well. We can have the pulse heating. No, not possible in this particular software. Need to upgrade the software for that.
All right. There's a query from Rohit Yadav.
In the DSC experiment, tell about the TX oxidation. So, is this peak same idea under DTA curve? See, DSC and DTA basically differs in terms of what is the information extracted. In DTA, it is the temperature difference, and in DSC, basically if it is a power compensation, then the power given to the sample, whether it is increased power given or decreased power given while there is a endothermic event. That physical parameter that is extracted, only that is the difference. Otherwise, in DTA as well as DSC, the same event is occurring.
In that answer,
that's it. Yeah.
Query. Any other query? Sir, there's a query from my side. Okay.
Yeah, sure, sir.
So, what is the material of the inert sample since it doesn't undergo any transition? What is it made?
It's the inert material that we are using. It is alumina powder.
All right. Okay.
Generally, any other material, for example, say gold, platinum, these are also used as an inert material.
All right. Yeah, thank you. So if there are no more queries, then we thank Dr. Chandrasekhar